Hello friends, in this video we are going to discuss about some preliminary topics of electronics device. This is the part 2 of the preliminary topics. So in these preliminary topics we are going to discuss about the electric field intensity, this electric field intensity is denoted by capital E in electronics device. Sometimes this electric field density or electric field intensity is also termed as field intensity or field gradient or only field. All these three words are same as the electric field intensity. Now, this electric field intensity is defined by, that is the mod of the capital E is equals to the ratio of magnitude of the voltage existing to distance or spacing. So the electric field intensity is defined by this ratio. Now the important thing is that the field always means the electric field direction, that is we can write the E direction is always from the positive charge or the positive polarity to negative polarity. Always it will happen. That means if we have a positive polarity here and if we have a negative polarity here, then the electric field direction will be from the positive polarity to the negative polarity in this fashion. Now let us take this concept to the semiconductor device. For that, let us consider a semiconductor bar. Let us consider this is a semiconductor bar or semiconductor material. Suppose this is a silicon semiconductor material, and we have applied a potential of some voltage across this semiconductor material, and the voltage is capital V. Now, due to this applied voltage, we can say that this terminal will be the positive terminal, so it will be positively charged, and this terminal is negatively charged. So the electric field direction inside this semiconductor will be in this given direction from positive polarity to negative polarity. So this is the electric field direction inside this semiconductor. Now every semiconductor will have some electrons and holes. So we can say that this electron and holes are there. Electrons and holes will be there. There will be so many electrons and holes. So due to this electric field, the electron will move in the opposite direction and the holes are moving in the same direction to the electric field. That is, electrons inside the semiconductor will always flow in the opposite direction to the electric field like this, and the holes will flow in the same direction to the electric field. So we can say that due to the electron movement in the opposite direction of the electric field, we will get a current due to electron in this direction. I am denoting it as In. So In is the current due to the electron, because current always flow in the opposite direction of the electron movement, and the for the movement of the hole I will get the current Ip, which will be directed in the same direction of the hole movement. So the total current that I will get will be moving from positive polarity to negative polarity due to electron and hole. I am denoting it as I total, and this I total will be constitute of Ip plus In. Ip is the component of the current due to the hole movement, and In is the current due to the electron movement. Another thing, if I denote this electric field with the applied potential, then it will come as E equals to minus dV divided by dx, where V is the applied potential and this x is the distance. How much distance is there in between the potential? So this is a very important equation which is relating the electric field with the applied potential, and this minus sign signifies that in the direction in which the electric field will be increasing, in the same direction the potential V will be decreasing. This is an important conclusion that we can draw, that suppose we have moving in this direction, suppose we are moving in this direction, then our electric field is increasing in this direction. Suppose now if we measure the potential value in this direction, we will find that it will decrease as we move from this point to the other point. That means in a direction in which the electric field will increase, in the same direction the potential value will decrease. It is the physical significance of this negative sign. Now let us take an example of the electric field intensity cases. So for that, let us take a semiconductor bar like this. This is a semiconductor bar, and we have applied a potential in the external way of 1 volt like this. So this is a semiconductor bar, and we have applied a 1 volt of potential. So in this semiconductor bar, if I define 3 points, suppose this is the first point A, this is the second point B, and this is the third point C. This A point has a value of x, that is the distance value is 0. This point C is at a position of x equals to 0.5 millimeter, and the point B is at a distance of x equals to 1 millimeter. So these are the 3 points situated at different position, and the A point has a position value of x equals to 0, C point has a position value equals to zero point 0.5 millimeter, and B point has a position value of x equals to 1 millimeter. Now, if we want to find the magnitude of the field at B position, then so we can write that magnitude of field, that is the electric field at B position, we can write it as EB, that is the electric field at B position mod will be given as V, or the potential at the B position, that is VB, divided by the distance x. So the VB potential, that is the potential at this B point, will be 1 volt because I have applied 1 volt here. So this 1 volt, and the value of x, that is the position or distance, is 1 millimeter. Now I can write this 1 millimeter as 1 into 10 to the power minus 3 meters. So it will be 10 to the power 3 volt per meter. So this is the value of the electric field at the position B. Similarly, if I want to find the value of the electric field, that is the magnitude of the electric field at C point, then I can denote it as EC mod. It will be equals to VC, that is the potential at C, and the distance of the C point. So from this picture we can see that the potential value at this C point will be 0.5 volt divided by the distance value is 0.5 millimeter. So I can say it will be 0.5 divided by 0.5 into 10 to the power minus 3 meter. So it will come out as 10 to the power 3 volt per meter. So you can see that at the C point the electric field value is 10 to the power 3 volt per meter, and the B point the electric field value is 10 to the power 3 volt per meter, and all these value are the magnitude value, so it will be mod E. So electric field will be constant. The value of the electric field throughout the semiconductor will be constant due to this 1 volt potential. Now if I want to draw a plot of electric field with the position of the points, then I can draw this graph like this. In the x-axis we will use the x value, that is the position value, and in the y-axis we will use the electric field value, and we have denoted the electric field, that is the magnitude of the electric field, as E. So this electric field value is constant throughout the semiconductor bar. So the plot will look like this. It will be constant throughout the semiconductor bar, where this is the x equals to 0 value, and this is the A point, this is the C point where x equals to 0.5 millimeter, and this is the B point, that is x equals to 1 millimeter. Now what will be the value of this electric field? inside the semiconductor, it is uniform and the value is 10 to the power 3 volt per meter. Now, if we want to find or if we want to plot the value of the potential with the distance, it will look like this. In the same graph, in the black color, I can draw the potential value, that is the V, in the y-axis and X in the x-axis. So, if I plot the V value with the position X, we can see that at X equals to 0, the potential was 0, and at X equals to C, the potential is 0.5. So I can draw the graph looking like this. So at C point, the potential value will be 0.5 volt, and at B point, the potential value will be 1 volt. We have seen that. So the black one is the potential plot, and the blue one is the electric field plot. In the electric field, you can see it is a uniform plot, but the potential plot is linearly increasing plot with the position. So this is all about the electric field intensity inside the semiconductor bar. Now let us see another preliminary topic of the electronics device and circuit is the current. So let us discuss about the current. That is, this current, we know that it is denoted by the alphabet I. So I means the current, and this I is defined as the rate of charge flowing through the semiconductor. We will consider the semiconductor because we are studying the electronics device. So current is nothing but the rate of charge flowing through the semiconductor, or we can say that rate of change of charge. Now we can write this I in equation as rate of charge that is changing means the charge that is changing with respect to time, that is dq by dt. Change of charge with respect to time, per unit time. And this equation is the equation for the current inside the semiconductor, and we know that inside the semiconductor the current will be due to both holes and electrons. So we can say that in semiconductor the current I is a bipolar current because the current is due to both electrons, negative charge, holes, that is positive charge. That's why the current inside the semiconductor is called the bipolar current. So this is all about the preliminary topics part 2. Thank you.